Now we're looking at Bohr's third postulate, which is for the energy that you would get for the photon during a transition. And we first think about what the total energy of the system is, where we've got this electron orbiting at a certain radius r, and it's got total energy E, which is the kinetic energy of that electron plus the potential energy of the system. And this is a non-relativistic orbit of the electron, where v is the orbital speed, and so the kinetic energy is just 1/2 mv squared. M is the mass of the electron, and we have the potential energy, which is the Coulomb electrostatic potential, and that is it's a negative because we've actually got this negatively charged electron, positively charged proton. So you'll remember this from last semester from your electromagnetics, that this is some constant Ke times the charge of the electron squared divided by r, where E is actually, if the absolute value of it is the same for the proton and electron, and that's actually why it's E squared. So we've got two variables, V and R, that we don't know, and we have one equation. So we need another equation. And the other thing that we can look at are the forces involved, because we have a nice radial force that the this diagram here on the right is showing us the inward force. You think of as, say, the centripetal force that's required to keep this electron in a circular orbit is exactly the Coulomb force, which again we know from electromagnetics. So we have that Coulomb force is this constant Ke times E squared divided by R squared. And this is equal to, now using Newton's second law, and the acceleration is v squared over r, we have this is equal to mv squared over r. Okay, so with those, we can solve for the velocity in this force equation, which is pretty straightforward. Or actually, it's more useful just to keep it as v squared. So this gives you v squared is equal to Ke E squared over mr. Okay, and then once we have that, we can now go back to the second postulate from Bohr, where we had the angular momentum. And the reason we're going to do this is that we'll see that we can actually solve for r in terms of constants and that quantized value, the integer value n. So let's go back to what L was. L was mv times r, which was then equal to n h bar. Okay, now if we solve for v in this angular momentum relationship, and again, actually v squared is more useful. So from this, we get v squared is equal to this nh bar over mr, and we have to square that whole thing. Okay, and we now see that we have these two formulas for v squared, so we can just set those equal to each other. So we're eliminating v, and we can solve for r. So that's quite straightforward. If we do that, we have n squared h bar squared over m squared r squared is equal to K times E squared over mr. And now we can see that we can solve for r. Doing that, we get r is equal to n squared h bar squared over mke e squared. So we see that all of that is a constant times n squared.